Chapter 9, Section 2 in your chemistry book. Shapes and properties of molecules. And now we know certain molecules have certain shapes. As they come together, they may be looking like a tripod, they may be equal, symmetrical, or they can look like they're going in one direction. They'll have north pole, a positive pole, and a negative pole on each side, and those will be polar ones, and we're going to have non-polars. So all these things, so we'll find out different shapes, and there's going to be specific shapes. These will probably be on your test too, these shapes on which molecules will have, these shapes. In the basically going by, we start with the Lewis structure, and these are the Lewis structure here. So the Lewis structure, it can predict how different molecules, or I should say atoms or molecules, may form covalent substances. So we're going to talk about covalent. We're not talking about ions now. We're talking about sharing. Covalent meaning sharing. And so we'll have some situations like this one here. We'll see they're basically, we're taking, for example, carbon has the Lewis structure of 4, and it can obtain an octet of electrons. It needs 8, so it needs to share 4 of them. So it has hydrogen, each has 1 to share, so we end up having this picture here with 1, 2, 3, 4, 5, 6, 7, 8, and that would be, this is one way to do the Lewis structure, or like this. Either way, you see the carbon sharing with all the hydrogen. And so nitrogen has the Lewis structure with 1, 2, 3, 4, 5. You see there, there'd be little dots, 1, 2, 3, 4, 5, and can form 3 covalent bonds to obtain an octet. So it will have, instead of just having 4 like carbon, it will have over here, it has like, it has 2 here, 2 here that they don't need to, not sharing, but they're sharing this one and this one and this, because nitrogen needs to have how many? It has 5, so it needs to have 3 more. So it needs to grab 3 more electrons from somewhere to make it 8. So now we have 1, 2, 3. It grabs 3 hydrogens there. So similarly, oxygen has the Lewis structure here, and it has 6, 1, 2, 3, 4, 5, 6. So now it needs 2 more. So here it has, basically is sharing, going to share those 2. So as it shares those 2, it's going to share hydrogen, share it. So I have 1, 2, 3, 4, and these two are going to be shared. So 1, 2, 3, 4, it's sharing this one. 1, 2, so it has 6, and it's sharing. See how it's same way as this one. We're talking about covalent. Covalent means sharing. So fluorine can form 1 covalent bond and hydrogen. So we have fluorine here, and it has 1, 2, 3, 4, 5, 6, 7, but it's sharing that 1, 7 with hydrogen, which actually needs 1. So that's how that looks in the midst of that. So let's look at that. Here's the picture of it right there. You see how the sharing goes. I kind of wrote the pictures there. So you have carbon. This is how carbon looks. This is how nitrogen looks. This is how water looks here in the midst of sharing in fluorine. So, and this one over here, of course, I didn't go over, is how sulfur in the midst is sharing with hydrogen. So there we go. So also elements in the same group, like this would be the same as this, right? Sulfur has the same amount as oxygen, so those in the same group would look exactly alike, like this. See, the oxygen looks like that, and there's a sulfur, so it's holding on to 2 hydrogens because it's in the same column. In column oxygen column, same column as oxygen. And so we have this and this, and they'll look the same. So kind of seeing how you do those Lewis structures there. So let's go on to here talking about delocalized electrons and covalent molecules. So a lot of time, especially in metals, we have all these delocalized, that means free electrons flowing through that are being shared between atoms. We know that especially in metals because that's what makes it metallic. But some other, basically molecules might look like a double bond, like this looks like a double bond in the midst of it, but really not, because it has a delocalized. It could either be look like this with the sulfur and the oxygen. They have a double bond here, a double bond. But when it comes down to it, they don't really they don't take that bond because they have delocalized electron pairs as they float. Lewis structures do not give the correct result because SO2 contains a pair of delocalized electrons that circulate freely. So this is making it even more complicated, but that's the way they go. So in the midst of this, delocalization is basically, what does that mean? Is bonding between two electrons are shared by more than two atoms. So you have more than two atoms that are sharing this. And here's a picture of delocalized right here. This is a good picture actually. So we have oxygen and we have sulfur and we have oxygen here. And you see the double bond here and the double bond. This is the way we would like to have it, but really it doesn't look like that. And this is how we think it would look, but because we have delocalized ions that are flowing, it looks like just one and then 1, 2, and then you have basically electrons just flowing freely like this through here. So in the midst of that, this is the way it really looks because it has delocalized electron pair. So this is in reality, this is in our form. We think, oh, it has a double bond. But really, it just has, instead of that one bond, it has electrons that are flowing. You get it? So delocalized electrons in other compounds. Here's another picture of ozone. This is ozone is oxygen 3, or 3 things of oxygen, 1, 2, 3. And again, it has delocalized ions flowing in between them. Here's benzene, another one. You see carbon and hydrogen. And so here we have the carbon molecules and we have all the hydrogen, but you also have delocalized in the midst of this delocalized. So it looks like it has a triple bond or bonds and everything, but really they're electrons that are flowing in between them. So that's all that delocalized means. It's just a bonding situation in which electrons are shared by more than two atoms. In the midst of this, when we're talking about delocalized, we also have down here, here's some pictures. Well, here's another example of delocalized with the nitrogen and oxygen. Here there are 3 different formulas you can have. You can have the double bond on this side, the double bond on this side, or the double bond on this side. But all of these, really, it's delocalized because this bond will flow from each side. So you end up having a delocalized type of happening there in the midst of that so-called double bond. Okay, oh, another thing, is it written down here somewhere? Let's see. Is this arrow. Whenever you have an arrow like that, it's called a resonance form, and it just means it's in between all of those. So it could be any of those forms. So if you have an arrow, that means, oh, it can look like this or it can look like this. And so that's the same for down here. You see what that arrow is? It's a resonance form. It could look like that, it could look like that, and it could look like that, depending on where those delocalized electrons are. They're just free-flowing electrons in there, like electricity. So molecular shape. Okay, here is what we call, basically we're going to take VSEPR, and what does that represent? Well, let's look to see what it represents. It represents V valence. That's a good thing. We're talking about valences. Those are those electrons in your outer shell. Shell, valence shell, and then electron pair. You have an electron pair, and repulsion, often pronounced Vesper, but it's VSEPR. And so it says, let's describe this. So Vesper, it predicts the shape. Vesper is the shape. That's what we're talking about. Remember, we want to know what the shapes are, right? We're talking about shapes. What kind of shape that molecule is going to have. It predicts the shape by bonding and non-bonding electrons, pairs in the valence, that pushes over different molecules into different shapes, pairs and shapes. So it sees these different pairs, and as some pairs have more electronegative values, which are stronger, they're going to push other parts into making the shape different, okay? I hope you understand that. That was kind of hard for me to explain, but the shapes. Here's down here. It's actually in these pictures better explained. You see here, okay, this is electron clouds of non-bonding valence, okay? This is just a regular carbon, okay? And so the hydrogens haven't attached yet. But in each one of these, you have, you can have 1, 2, 3, 4, 5, 6, but you have non-bonding that haven't bonded. But anyway, so in the midst of this, you are going to have unbonded carbon is still going to have that, that repulsion. So it's saying the electron clouds of non-bonding valence, this one's pushing this over to here. It turns out to 109 degrees instead of, so it's not just a square, it's going to be a little bit different by those unbonded carbon atoms. And so here we go again, same thing. If we put the hydrogen on there, it's going to shape and look like a shape like this. This is called, whenever you have 1, 2, 3, 4, it's a tetrahedra geometry. That's what it's going to look like as a tetra. So this would be CH4, and this is what the tetra would be. That's the shape it would be. It's going to look like that with 4, 1, 2, 3, 4, and that pushing of those into making that shape. That's what this VSEPR has to do, is making shapes, the VSEPR shapes. So this picture here is of another type of shape. Now, don't look at these orange one. All they are is that's the non-bonding electric pair and that strength. These are just forces. These two orange things are just forces. So we have a nitrogen that has 1, 2, 3. So it's going to look, and then the other two are going to be up here. The nitrogen will have 2 of them that are non-binding, they haven't combined, and these 2 will produce, basically pushing these others down at the bottom so it look like a tripod. So that's the shape of it's called trigonial pyramidal. It's basically a tripod shape. So that's the tri means 3. There's going to be 1, 2, 3 atoms combining with 1. So if you can guess which one's which. If it's a 4, it's going to be a tetra. If it's a 3, it's going to be tri. But there's going to be 2 different kinds of tri. One's going to look like a tripod, and the other is going to look like a plane. It's all going to be in one plane. So here we have the trigon pyramidal, and that will look like a tripod. And then we're going to go over to the other I just skipped over here. This is the trigonial planar. If you look in this geometry, it's basically, you have a barium and you have fluoride, but they're all the same. They're going to be equal distance from each other. So this will be a 120 degree angle. This will be a 120 degree angle. So it'll be all 360, and it's going to be in one plane. If you turn this over, it'd be just flat. As for the trigonium pyramidal, it's not in one plane, right? But this one would be in one plane. That's why they call it planar, in one plane, trigonial planar. So there's 2 different, with 3 of them, there's 2 different types. And then we have going on from that, we're going to also have angular. So when you're talking about angular, we're going to talk about why they produce an angle. They push to another angle. So this is when you have, angular ones are very famous with water, H2O. So the hydrogen oxygen atom has angular because you have 2 bonding pairs to 2 non-bonding pairs. And in the midst of all this will push it over to one side, and so that the hydrogen and oxygen molecule of water looks like it's at an angle. So let me show you a picture of that. It's easier for me to show a picture. So here, let's not look at these little non-bonding pairs because it has a pair here and a pair here. This is just the forces, like I said. Here's the oxygen, here's the hydrogen. Why are the hydrogen clear over on this side, like an angle? Well, because this pair, any electrons that are not paired have more power than electrons that are shared. So these have more power, so these are pushing these 2 hydrogens to this side. So you have the oxygen on this side, and it comes at an angle. That's angular. So remember, and it's only 2. So we know it's not going to be tri, it's not going to be tetra, it's going to be 2. And on to the last one, which is basically going to be linear. The picture of linear is that they're in a line, a straight line, so they're equal in that line. They're not pushing each other because they have been filled up. They have no, as you look here with the BE and the F, So as you look here, you see 1, 2, 3, 4, 5, 6, they're sharing. 1, 2, 3, 5, they're sharing 1, they're sharing 1. And in the midst of all that, it's equal. So note that Be, barren, has only 3 electron pairs in its valence shell. All of them are bonding pairs. So it only has threes, and they're all of them bonding. So it has no non-bonding pairs. So it's going to be very equal. And we call this, this one here, trigonium planar with pairs. This one here. A linear here is going to be the same way. Linear is going to be Be, and then it's going to be equal because it has no pairs, like pairs that are just non-bonding pairs. They're all bond up. I hope you get this. It's kind of a little bit confusing, but anyway, you need to know those shapes. So we're going to go over those shapes again. We have the tetrahedral shapes, which is a 4. We went over the 4 shape right over here. Down here, 1, 2, 3, 4, like the carbon and hydrogen. That'd be the tetrahedral. Then we'll have the trigonium, a 3 here, and then because you have a non-binding here, there's pushing these 3 down into like a tripod. And here we have the 3, but they're all equal. There's no force there because they're all equal, and barium doesn't have any non-paired. So because it only has 3 to share, so boom, 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 boom. There we go. We have this all in one plane. This one is all in one plane, and this one is like a tripod. They're both 3. This is the angular again, especially with hydrogen and oxygen, water. This is water, H2O. You can see here these two, because these are two non-paired, two pairs that are non-paired, but they're pushing them this way, and so you're going to have that angle. And then this here is just equal. So we have no forces pushing on these two. So they stay in one plane. They just stay flat. Okay, so you have these, this is how they give them shapes. So let's go on from that point. We're going to go on to the polar and nonpolar, which we already have talked about, but you're going to go back to it, and they're going to show you some more things about polar and nonpolar. So here's at the bottom here. Do you see this picture at the bottom? So polar and nonpolar. Remember, it's important to know if a molecule is polar because this affects what forces attract them. Because a polar has one side that's, one pole, I should say, that's going to be negative and one pole that's going to be positive. And so it will react different, and it will want to bind with certain other molecules because it has a positive and negative side. That's polar binding. A molecule that's asymmetrical, that means asymmetrical, it's not equal. It will probably, much likely, of course, if it's asymmetrically, have no dipole. So it will be, so if it's non-symmetrical, it's going to be polar. It would be more polar. But if it's symmetrical, it's equal on all sides, then it doesn't have, a side that's negative and a side that's positive, and that would be nonpolar. So nonpolar. Just remember, if nonpolar means it's all balanced out. It doesn't have a positive or negative. So, and here's a picture. Carbon dioxide in linear model has 2 polars, and you can see that, and it's basically equal on each side, and it's basically, as you go one direction, is a linear model that has 2 polar carbon oxygen bonds on it. Okay, and that's how they represented it there, just with those arrows. Okay, so since they're equal, so carbon dioxide is a nonpolar. It doesn't have poles. Carbon dioxide, kind of nice to know. On the other hand, ammonia here has a trigonial pyramided shape, kind of like that tripod, right? Like a pyramid. And now you have nitrogen, which it's going to combine with hydrogen, and then it has the 2 non-binding there. So it ends up pushing these hydrogens this side, like I said before. And of course, this is going to be polar. It's going to have one side that's going to be positive and one side that's going to be negative. So it's going to push, the hydrogen is going to push this direction. So it's going to have a very polar, and this will be pushing up to nitrogen. See the arrow going in this direction. So in contrast, BF3 is going to have the planar type, like they showed, is going to be different. It's all going to be symmetrical. There's no extra, as for being polar or non-polar, there's going to be no bonds here. So in the midst, it's going to be symmetrical. So we know if it's symmetrical and has 3 equivalent BF bond, that they cancel each other out, and that is going to make that non-polar. There's not going to be a positive or negative side there because it's all equal, right? So I like what it says here, and it describes things better. It basically says it's like a tug of war. 2 teams are pulling opposite directions. So, and that's like in CO2. CO2 where we had before. Let's see, let's go back to CO2. So we have CO2, they're pulling in opposite directions, and they're canceling each other out, but they're still pulling, right? And so when you have 2 that are stalemating, they're going to be nonpolar because, they're going to have no pull because they equal. And then in the BF3, this one here, they're going to have pulling on all. This one's pulling, this one's pulling, this one's pulling, but they're all going to be equal. They're equally pulling each other. So they're going to be very symmetrical. So there's going to be no net dipole. There's not going to be a positive or negative. And this one is going to be nonpolar. But when we go back to this one here with nitrogen and hydrogen, you see it's going to be, the poles are making it asymmetrical. It's not symmetrical on one side. Of course, this side up here has nothing, right? So this bond is going to be very polar. It's going to have one positive side and one negative side. You see those pictures? Okay, let's go on to the concept review here, and then we'll be finished with this chapter. What are delocalized electrons? What do you say? They're free electrons that are not localized. Delocalized means not localized. So they're free electrons that are flowing between more than 2 atoms. Just think more of 2. Sometimes a lot. With metals, a lot of them, a lot of atoms. But it has to be at least flowing between more than 2 atoms. So on to what term refers to a situation in which electrons are shared by more than 2 atoms. So if electrons are shared by more than 2 atoms, of course they're covalent bonds. Of course, when you share means covalent. But if they have more than 2 atoms, they're basically called delocalization. So number 1 answers number 2, What is meant when a molecule is described as being polar? Polar means basically that it has more electronegative on one side than the other side. Or you can say one side has a positive side and one side has a negative side. So it has a positive pole and a negative pole. That's polar. Let's go to the application here. What shape would you expect a molecule based on an atom with only 2 bonding pairs of electrons to have? Okay, what are those shapes? We had those shapes, right? So let's look. So let's look back at those shapes. Okay, so if it has just two atoms, you're going to have linear. This has 2, 1, 2, or you're going to have angular. These 2. So you'll have for 2, you'll have linear or angular. So if you have 3, what are you going to have? You're going to have trigonial, planar, it's all going to be in one plane, or you're going to have a tripod. These are the 3. And then of course 4 is going to be tetra, remember? So we had that picture of tetra too. So okay. Based on the Lewis structures you have already studied and the group similars, remember the Lewis structures are those little dots that are around them. And the group, give the Lewis structure and the shape of each of the following molecules. So I'll have to show you that. So let's see if I put it on here so you can see it. Because otherwise I'm not going to be able to describe it to you. Okay, Okay, here we go. It's kind of shining through there, but here's the Lewis structure of SiH4. So you have Si and then you have the H's. So what would this be? Tetra, because we have 1, 2, 3, 4 hydrogens. 4 hydrogens will make it tetrahedral, right? Tetrahedral. A, you have aluminum fluoride, and so you have 3. So it's going to be one of the tri because there's 3. But as you see here, you have we'll have aluminum and you'll have these 3. It's going to be triangular planar in the midst of this with aluminum, and looking like that. Then we have hydrogen sulfate. It's going to be very angular. It's going to be just like oxygen because you have 1, 2, 3. You have these 2 at the top. They're pushing these 2 down. So it's going to be very angular. It has 2 angular. Here's hydrogen bromide, and bromide being 1, 2, 3, 4, 5, 6. It has 2 here with hydrogen. This I had as linear. I am, just because if it's 2, it's only going to be in 2 planes, so linear. So now we have Se, selenium chloride, and this 2. This is what I put here, so this is what it looks like. You're going to have Se has the 2. It's going to share the chlorine this side. It's going to share the chlorine on this side. So in the midst of this, it's going to be angular because it has these 2 in the top, these nonpolar ones in the top. And so it's going to be angular. First I put tri, but there's only 2 chlorines, so it has to be either angular or linear. This one very much is angular because it looks a lot like the oxygen. So here we have oxygen down here at the bottom, O3, which is the ozones, so the 3. It's going to be trigonial planar because they're all kind of equal, but they're all on one plane. They're not pushing it apart. So we have these together, trigonial planar. And down here, phosphate iodine is going to be a pyramid because it's going to look like this. You have the phosphate up here, and there's 2 extra up here, and these are pointing down. These are pointing down, 3 different. So it's going to be like a tripod. So we call that triangular pyramid right there. And down to the last one here, we're going to have CCl4. And of course there's 4, that's the clue. So you have chlorine, chlorine, chlorine. So we put this together, and they're sharing all the way around here with the carbon. You have carbon sharing like this. It's going to be tetrahedral because there's 1, 2, 3, 4. Okay. The last question, what conditions must exist for a polyatomic molecule to be non-polar? So for a polyatomic model, that means it's going to polyatomic molecule. It means that to be non-polar, all of the poles have to be symmetrical. So it's going to have to be hooked in a normal, like they're all going to have to be the same, like a bunch of carbon and hydrogen molecules all the same. They're going to all have to be the same and be symmetrical to be non-polar. So otherwise they would be polar, it'd have a positive and negative. But for a polyatomic molecule, they all have to be symmetrical in a line, basically in a line, which a lot of them are. So anyway, so I'm going to go on to the next section. I think you got this section, hopefully. And I wanted to go over the quizzes. I'll do them together after I finished, and we'll go through the quizzes really quickly. So.